In this screencast, I'd like to explain how to realize digital systems using NAND only or NOR only gates. Why is it important? Because NAND gates and NOR gates are generic ones, which are cheaper in CMOS realization, CMOS implementation technology, cheaper than their counterparts AND and OR. So instead of using ANDs and ORs, it is wiser or cheaper to use NANDs or NORs, okay? Because these gates are cheaper in CMOS. Okay, so I propose to do it using an example. Design a system that tests if 3-bit input number in binary is divisible by 3 or 2 or 3. And the truth table is already constructed. You can see it here. And as you can see, and I hope you can easily verify that the y is 1 when this condition is satisfied, divisible by 3. 0 is divisible by 2, 3, any number, so it is 1 on the output. 2 is divisible by 2, 3 by 3, 4 by 2, 6 by 3, and also by 2. But the 3 cases are not divisible by any of the 2 numbers, 1, 5, and 7. So next step is to derive truth table kernel map to minimize this. So let's locate only zeros, okay? This will be faster, and then put everywhere in the remaining ones, in the remaining cells ones. 0, 0, 1. 0, 0, 1, as you can see, x2 is here, x1 is here, 0, 0, 1 is here. So 0 is here. Next 0 is 0, 1, 0, 1, so it's 5. 1, 0, 1 is here, 0. The second one, the second 0, and the third 0 is for 3 ones, so for 7 is here. Also remaining are in logic 1 state, okay? And let's decide that our first goal is to realize the system using NAND gates. For NAND gates, it is a also wiser or better approach to minimize for ones as we did before. So we combine ones, and there are 2 groups, and the first is the 4-element group. So y is equal for this group, only x0 doesn't change, so that's why the symbol trivial product, not x0, is here. Then you must add second group is here, and the product, in the product you've got x2, which must be inverted, times x1 without inversion. So this is the minimized version, and what you do next is to double invert the whole expression, double invert the whole expression, okay, and then use the De Morgan's laws to transform plus into dot, so sum into product. So if you use De Morgan's law, you get something like this. Of course, the external one you leave it without any changes, and from the lower one you use De Morgan's law. So it is the product of the inversions. So the inversion of not x0 is x0. Instead of plus you've got times, okay, so product, and then you must invert the second expression, the second element, and you did it, okay. You do it in this way. So what you've got is a NAND. It's also NAND, and NOT is needed here. So if you have only NANDs, so the proper way, one of the 2 possibilities to get NOT using NANDs is in this way. You simply connect the 2 inputs together to have an inverter. But very often, because NOT is cheaper than NAND, you've got at your disposal also nots. So let's do this in this way. So you must implement this function using not. You've got not here. It is x2. x2 must be multiplied with NAND, with x1. And then this output from this NAND is fed to another NAND. And the second element, the second input variable for this NAND is x0. x0. So you've got y. It is a NAND not implementation of this system. Okay, it is a decoder or detector of divisibility by 2 or 3. So a cost factor. A cost factor I am introducing now. A cost factor consists of two numbers. And the first is the number of all the inputs of all the gates. We are counting one input, second, third, fourth, 5. So the number of inputs is 5. How many gates is the second number? How many gates are there in the implementation? 1, 2, 3. So the cost factor for this implementation is 5, 3. Okay, let's do the same for NORs. For NOR implementation, I will need, or it is also a better approach to minimize using zeros, not ones. I am doing this for the first time in the mini lectures. 1, 1, 0. I simply copy this table, but instead of combining ones, I will be combining zeros, and the rules for the obtaining y is different. I will explain it in a minute. The bigger group of zeros is 2. So from this, you've got, instead of product, you've got a sum of the variables which don't change. Which one don't change? x2, because this is equals 1, so x2 plus, not product, not times, but plus. And the second is x0. x0 is also constant for the two. Okay, and what is very important, the rule of putting dashes is different. When the variable, as in the previous one, when variable is equal to 1, you must put dash above it. Okay, the same is true for x. So the solution is this. For this group, it is the first sum times the second sum is we've got the second group of two neighboring cells and the toroidal neighborhood, and which ones are constant, and x0 and x1. x1 is equal to 0, so without a dash, the opposite rule. And because x0 is 1, you must put dash. Okay, so instead of having sum of products, you've got the product of sums, and the rule of for putting dash above the symbol of the variable is also different than before. So what are you doing now is I will wipe it. Okay, if you've done it, I mean, you've got the minimized version, you do the same. Simply invert twice. If you invert twice, the function is still the same. And use the Morgan's laws, the second Morgan's laws, as the complementary one, to transform this product into plus. Okay, because NOR, it is NOR implementation. NOR is simply the gate of the sum, inverted, but the sum, not product gate. So you've got something like this, not x plus not x0 inverted plus x1 plus not x0 inverted. It is an internal inversion, lower one, so, but the upper one is left without any changes. So you've got the NOR implementation. I will draw the diagram in green. Okay, for NORs, you've got something like this. You've got the output NOR, and two previous ones. Each one has two inputs. Okay, and you've got also nots, because you need x2 and x0 have x2 and x0. You've got x, let's say it is x2, and next you've got x0 here. x0 must be fed in the second, because you've got also not x0, and x1 is the third variable. That's all. Cost factor is bigger than in the previous case. Here you had 5 inputs. Now you've got 1, 2, 3, 4, 5, 6, 7, 8. Quite high number. And the number of gates 1, 2, 3, 4, 5. So first, if you are looking for the cheapest solution, you must verify or implement in 2 ways. First, find the NAND implementation, then NOR implementation, and compare the results and choose the cheaper if you are, of course, interested in it. Okay. Of course, in the real world, the cost depends on many factors. Yes? For example, you don't have any NANDs at stock. Okay, but you've got the many NORs in the stock, and you use it even if the cost factor for implementation, for NOR implementation, is bigger. All right, so in real life. But for our case, I mean for this course, we'll be using a very simple academic cost factor, okay, only to compare the implementation. So do it the same, yeah, the 2 minimization, and remember, if you have a free choice, please minimize for ones if you implement in NANDs, or minimize for zeros if your implementation is in NOR gates. Okay, it is a wiser, cheaper, and of course, even if you have a sum of products, you can transform it into NOR and NANDs. That doesn't matter. Okay, so but I will show you in the following screencast or during the lectures in class. Thank you.